Okay, ultraviolet catastrophe. What do you know about the ultraviolet catastrophe? Something, a little bit, or nothing? Oh man, that's a catastrophe. Okay. Uh, Ultraviolet catastrophe is something like this. Now let's just say we got a string. And we do the fundamental mode of oscillation. And that's a potential mode of oscillation, right? And then we can go to the second mode, which kind of looks like this. Then we go to the third mode, not particularly well drawn, but sort of looks like this, right? If this goes on forever, it's a catastrophe. It'll have infinite energy. But there's no reason this can't go on forever if we have an ideal string. Wavelength get as short as possible. Short as we want. You know from the set 6 on waves how to get the energy of a wave, right? And that's just a suggestion that you make sure you do know how to get that. Okay? Energy of a standing wave. So, you know, and I just make that as an annotation. It's something you need to understand. And it simply comes down to every point on every one of these is undergoing a simple harmonic motion. Okay? Greater the frequency, to get greater frequencies for a given string, you're going to have to wiggle it faster, which means that simple harmonic motion is going to have more and more and more as we go down the list, more and more and more energy, right? And just add up all the simple harmonic motions of all the points of a standing wave. So it's something probably want to review. As I say, what we're heading for just kind of really touches on a lot of things we've done this semester. And then some stuff from first semester. I mean, stuff on modern motion is first semester. People did pretty well on that. So should be able to understand it in terms of the wave. Okay. Now, black body radiation. And there are a lot of things that I'm not going to be able to say about these things. So another thing that you might consider doing is taking a look at what AI has to say about some of these things. It'll give you really good information. Now, if you go too deep, it might start making things up, but you're probably not going to get that deep. And I'm not sure I could get deep enough into it before it starts making things up. But somebody's an active researcher, you know, could probably eventually get to the point where it's going to lie to them. Might not be that case in a year. Right now, that is. Okay, so black body radiation, what do we mean by black body radiation. It means, let's make sure I'm recording here. Okay. It means that if you've got a piece of metal, like we heated up in an experiment, okay, or just add a whole chunk of metal, okay, that chunk is very close to being a black body, and meaning that most of the heat energy that gets, most of the radiation that comes from the inside of it, infrared radiation and so forth, gets through the surface. Or if you put it out in the sun, most of the energy that comes in from the sun gets into it. It doesn't reflect much, even if it's painted black. I mean, even if it's not painted black. Okay. So just imagine a piece of ideally black material that absorbs all the radiation that comes into it, all the radiation from the sun or from infrared or from ultraviolet or whatever. Okay. Now, what we observe is that the amount of energy we get, this is not a good curve, but the amount of energy we get for any interval, you know, I was going to try to hit those two lines, but I couldn't. This area here is maybe, what do you think? Is it more than 1% or less than 1% of what's under this curve? How many think more than 1%? How many think less? Only one person's thinking. Well, that's unlikely. No, I know you guys. Okay. I think more than 1%, more than 10% or less. I go with less. Okay. If I cut this thing out and it weighs 20 pounds, how much does this weigh? Just this region under here. Does it weigh even a pound? Maybe it weighs a pound, maybe not. Okay, well, I'm going to say it's maybe 3%. You might think it's higher, and you might be right, of the total. Okay? And I've labeled this axis energy. Just kind of think of energy and wavelengths as kind of being synonymous. And I won't even try to explain why I do that, but and it's actually frequency. You understand these waves are higher and higher frequency. Okay? Energy is the area under this thing. If all frequencies are permitted, then let me draw a picture here. Here's a black body chamber. Within this chamber, you can have waves that resonate like this, or you can have waves that look like this. But of course, you can have waves up and down, that look like this, just these things, and also waves that go diagonal and bounce around and reflect off of corners and edges and everything. Okay? Now let's say it's a vacuum in here. And the walls are all heated to some temperature. Okay? Then you ought to have all wavelengths present, including the really short ones that have a huge amount of energy. Okay? This model implies graph looks like this. Infinite energy. Okay? You integrate this thing from negative infinity to infinity. Well, it goes to zero out here before too long. And actually, you can't go from negative infinity to infinity. You go frequency zero to infinite frequency. Okay? So it'd be an infinite interval. This would be an infinite interval. It's always increasing, which is going to be a catastrophe because you got infinite energy. Okay? This is reality. Total energy is finite. Now, I'm oversimplifying it. This is electromagnetic radiation. Electromagnetic radiation, well, we'll talk a little bit more about that because we've basically developed Maxwell's equation by this point in the course. I'll describe a little bit about how Ampere's law and Weissevart and Coulomb's law and everything, and flux changes and creation of electric and magnetic fields create an alternating electric and magnetic field that propagates at the speed of light, and that's what allows you to see. That's what our eyes pick up. Okay, it's electromagnetic radiation. The electromagnetic radiation you get in here, according to the theory, it was pretty well developed 150 years ago. Really well developed. Okay. That's what the theory predicts. That's the ultraviolet catastrophe. Predicts infinite energy in a black body. Okay. Okay. And that's a problem. People didn't know how to get around. Okay. Max Planck. Energies are quantized, electromagnetic energies, in a situation like that. E equals HF is photon energy. H is Planck's constant. F is frequency. The energy of a photon I think I remember this correctly. The units are correct, joule seconds. And I think it's 6.64, I'm pretty sure of that times, and it's a 10 to the negative 34th. If you read theories of space-time and stuff like that, some people hypothesize that there's a Planck length that's on the order of 10 to the negative 34th meters. Okay, the smallest length that can exist in strings that make up matter in the universe and so forth and energy. Okay, so and that's something I don't understand particularly well, except just conceptually. Never tried to work with it. Didn't know enough to start really. Okay, so you get E equals HF. That's your photon energy, and it can only have those values, which are multiples of this. So the minimum energy of photon well, there's no minimum. But if you allow this quantization through details that I'm not going to go over right now, okay, I'd have to think them through. I'd probably screw something up. I just decided to do this 2 hours ago. Okay. I've been playing around with the idea. Haven't had a chance to think it through well enough to describe the details. By this hypothesis, you explain this curve as opposed to this one. You don't get this one, you get this one. Okay? You can look up those curves, it's all in your text. But you probably don't have time. If you're interested, you look up, let artificial intelligence tell you something, give you references or whatever. They do want you to research and fill in some of the blanks. And that's another thing is when you use artificial intelligence to learn stuff rather than to not learn anything and dumb everything down. Okay. And we've talked about that a lot, and I think y'all are on track with that. Just make sure you stay that way. Because otherwise, what you know is not going to be worth anything. It's really what you're up against. You got to be able to work with artificial intelligence. Before you can work with it, you got to know some stuff. You won't know what to prompt it for. You don't understand all that stuff. You won't know when it's lying to you. You won't have the knowledge base you need to creatively use what's available. Okay. And the better you learn it, the better you will be able to deal with it. Which is a positive way of saying it rather than saying, watch out, it's going to get you. Okay. Everybody's aware of that. The positive side of that is it could be really good. Of course, Anthropic just came out with something that they're not going to release because it's too dangerous. Could escape into the wild and destroy everything. So they're not going to release it. Though they got some assurances, it's scary stuff. There's a huge potential for disaster, for catastrophe, and a huge potential for benefit. Stuff turns against us and it's in the wild, we better have something else to fight it. It's not going to be us. Okay, well, scary news aside, let's see what this has to say about the hydrogen atom. Okay? There's an N at the end of hydrogen. Bohr model, very good, great model. Bohr was one of the greatest physicists of all times. He and Einstein had wonderful debates. They were titans. Okay, came up with this model. And here's a proton. Now, proton is approximately 1,800 times as massive as an electron. So you got this electron. And let's go ahead and give these things colors. I'm going to go with orange and blue. Those aren't the right colors. Okay. You assume the electron is in a circular orbit about the center of mass of the proton-electron pair. Since the proton has nearly 2,000 times the mass of the electron, center mass is essentially just the proton, okay? So it's like, proton might wiggle a little bit, but they don't really do this anyway. Really, what this circular orbit is to the best we can describe it, it's a quantum mechanical phenomenon, and it's a probability distribution. However, if you think of it, so you think if you use this orbital model, you get some really good prediction. You can predict most of what we can observe in this lab. Probably everything we can observe in this lab. We can observe spectral lines and stuff like that. Yeah. Okay. If this is the case, and this is what you would expect, if you got electrons zipping around at various speeds and protons sitting there, electrons would start orbiting protons. Well, when they're orbiting, they're accelerating. And what's an accelerating electric charge do? It creates electromagnetic radiation, which means it loses energy, which means that pretty soon all your electrons that spiral into the protons go up in a burst of energy, okay? Or at least create neutrons and other subatomic particles. And there are many of them. That wouldn't work, okay? Well, Bohr said, okay, well, yeah, we see that it's something like another catastrophe. Yeah, electrons orbiting protons are going to lose energy because they're going to emit electromagnetic radiation. Of course, if they're going to emit electric radiation, it has to be quantized. So the frequency of this thing is going to be related, Planck's constant, and it's going to be limited by the fact that you're only going to get a certain frequency, so you can only emit a certain amount of energy, but it's impossible to emit that amount of energy. Something like that. Now, if Bohr was here, his head would explode upon hearing what I just said. And he was a kind of a good guy. And I wouldn't want to explode his head. Circular orbit. Now, key is, well, one is not really an assumption. The centripetal force, just like for a satellite around a planet, is the attractive force, okay? For a satellite around a planet, it's a gravitational force, gives you orbital velocity, orbital kinetic energy, all that stuff we studied 4 months ago, okay? or more like 5 or 6 months ago. Um, in this case, it's a Coulomb force, the attraction between the proton and the electron. Make sense? So that's a no-brainer. If you just pull out the circuits that you used in orbital mechanics, okay, it'll make perfect sense. Okay, the other assumption is orbital momentum is a multiple of h bar, which is just Planck's constant divided by 2 pi. And we got a question, so let's stop for a second. Yeah, the question was, is that orbital momentum or angular momentum? Well, it's the angular momentum of the orbit. So I can use the word orbital here. The angular momentum of this motion, which is I omega, moment of inertia times omega. Moment of inertia is just the mass of the electron times r squared, mr squared, okay? But we're going to use well, okay. I is mr squared. Omega is v over r. So I omega is just mvr. Everything's nice and perpendicular, so you don't have to do cross products or anything like that. Okay? Now, as I said, I had a good night's sleep. It was split between 2 nights, about half each night. So I'm neglecting to write down a couple of things. It's an integer multiple, so I'm going to have to. You can't read it, but it's there. So now I'm officially correct. It's an integer multiple. And I take care of that just by saying n is 1, 2, 3, and so forth. Okay. Okay, well, you can put these into symbols. So we have k q squared over r squared. Which is equal to mv squared over r, which except for the k and q, if q was mass of the Earth times the mass of the satellite, and k was big G, you'd have gravitational attraction. These are obsolete charges. There's the centrifugal or Coulomb attraction. Okay, and this is otherwise identical to what you saw to find the orbital velocity at a given radius, the circular one. Okay, so that's this thing, and then MVR equals NH bar. you solve for possible values of R and V. You could, for example, solve this equation for V and solve this equation for V. Set the two solutions equal and solve for R. Now there's eliminate V. Or you could solve this one for V, and that would involve R, and solve this one for R, and plug that in for the R in this equation. Get V as a function of R, but you're always going to have that NH bar there. In the result, and you could go through the details. I'm not going to write out the details, they're straightforward. Okay. You get these formulas that look kind of complicated. If you understand this and understand this, there's nothing complicated about it. So I recommend that you solve these. I could give you these two equations and ask you to solve them on an exam. Okay? It's just straightforward algebra. Make sense? Okay. When you do this, orbital energy is U plus K. And just like for satellites, the potential energy is going to be measured relative to infinity, and it's going to be negative. The closer you get to the proton, the more negative the energy is. Okay? Which means that the energy out further from the protein is higher. Proton. I try not to eat those things. Okay. They charge you up. Further you are out, higher the energy. Because the energy reaches zero the energy approaches zero as you go to infinity, the energy is real negative. We're in a potential well here. You're down the well, you're trying to get out. Okay? You get out, you need energy. You need to add energy. Okay, I can say a little more about that. I'll just say by the side, if a photon comes along and hits this thing, you can raise the orbit. Okay? We'll talk about that. Okay, anyhow. U plus K, it's negative, approaches zero as R approaches infinity. Okay? And that energy is proportional to n squared. There's a reciprocal n squared. Um, Your minimum R occurs for n equals 1. R is approximately, I think it's 0.529 angstroms. An angstrom unit, well, this is about half an angstrom. Okay. That means the size of the hydrogen atom, the diameter of the hydrogen atom, is about 1 angstrom, right? Radius is half an angstrom, a little more than half an angstrom. Most atoms have effective diameters, whatever that means, around an angstrom in their ground state, unless they're excited. Okay. And that includes atoms with 92 protons, the highest number that naturally occur. And it's going to have 92 electrons, but those protons are pulling them in so hard that still everything's compressed to within a radius on the order of an angstrom. Okay? Kind of interesting. Energy is negative 13.6 electron volts. An electron volt's the potential energy of an electron if it discharges through 1 volt. Take an electron at negative 1 volt and let it go to a screen down here at plus 1 volt. Okay, or at 0, ground, whatever. Electron going through 1 volt is an electron volt of energy, and you can calculate that because you just multiply the volt, which is joules per coulomb, by the number of coulombs in an electron, right? That's 1 electron volt, which is therefore 1.6 times 10 to the negative 19th joules. Negative 13.6 electron volts is therefore going to be about 10 to the negative 18th joules. Okay. Actually, it's going to be more than that. It's going to be, brain isn't working with numbers. I'm going to do that right now. 13 times 1.6 is about 20. 20 times 10 to the negative 19th is 2 times 10 to the negative 18th. Okay. You can do that in joules. The speed, well, the first problem you see in the introductory problem set, I think, asks you to figure out what the speed would be. Okay. Now, in the introductory problem sets, it says, okay, you're in a circular orbit, hypothetically at some random number. Okay. Well, the minimum R is for n equals 1. Let's call that R naught. And then R sub n equals n squared R naught. Okay. And if you figure out the velocity and the way that's related to this, you get the end of the negative 2 thing. 1 over n squared. It just comes right out of solving these things. You want to solve for velocity and then square it to get the kinetic energy. It just pops right out. So here are your premises, and all the rest is as follows. Solve this for R, you can use a known value of H bar Q. You get the relationship between mass of the electron, which is about 10 to the negative 30th kilograms. Better approximation is 9.11. Remember 911? Okay. Not y'all weren't alive then. Not even maybe. But uh, that's kind of easy to remember, although the connotation isn't a great one. It's 9.11 times 10 to the negative 31 kilograms. That's all in the introductory problem sets. I'm not going to write it down. Just kind of telling you where this stuff is coming from and why in the world you're seeing it. At that point, it's easy to do those calculations and answer questions. Okay, I say, okay, let's say you have an orbit at 1.8 angstroms. Okay? If an electron was orbiting at 1.8 angstroms, would that be a possible orbit? Would it have angular momentum nh bar? Turns out it wouldn't. Okay? The only orbits that are going to work are squared integers times this 0.529 angstroms. Now, what does this have to do with waves? In the first place, quantum mechanics is basically about quantum waves, or probability waves, probabilities of finding things at different points. But here's what it has to do with orbits of hydrogen. Okay, you got the energy, which is hc over lambda. Chalk has a bad spot on it. I gotta do something about that. See if I can flip it around. I probably already did. There's a bad spot on this end. Oh, you solve this for lambda. Get lambda equals hc over the energy, okay? This doesn't work for just any energy because it doesn't work for just any lambda. If you calculate the velocity you should have in an orbit of this radius, any old r, the value of r implies the value of v, which implies the energy. And actually, you got to take account of both the potential and kinetic energy. U is the potential energy, V is the velocity, you do 1/2 mv squared, and you get the kinetic energy. Make sense? Yeah, that's I found a little hard to understand when I first encountered it because the diagram looks too weird. I just couldn't reconcile the diagram. This has to be a standing wave. So it has to be a standing wave with wavelength lambda h equals hc over E, E being the total energy, potential plus kinetic, and not difficult to solve these things, okay? What's that look like? Standing wave. Maybe it's a standing wave consisting of three wavelengths, okay? What's that look like when you wrap it around into a circle? Okay, well, take this wave and wrap it into a circle. I'll draw the circle fairly big. It's going to look something like this. Now I'm wrapping a different wave, but you can see how if you wrap one of these around a circle, it might look something like that. That makes sense? And you've got what? One wavelength, two, three, four, five. I didn't draw, I fudged a little bit. I didn't draw it real well. But you see, you got five oscillations around this circular path. And the circular path is just this linear string wrapped around in a circle. Only certain R's make this so. Okay. Big deal. 2 pi r, the circumference, in order to have a standing wave, has to be keep forgetting to write integer, has to be an integer multiple of the wavelength. First several problems in set 7 deal with details of this picture, which you won't understand until you work through some of the details. But I want you to think in terms of the big picture and see how the details fit in to make it all work. Okay? And the details aren't that difficult. If you take those two equations, quantization of angular momentum, mvr equals nh bar, and Coulomb force equal centripetal force, K q squared over r squared equals mv squared over r. Okay? Simple enough equations, easy to understand if you understood first semester gravitation equations. And just do some algebra 2 on it. Then you get things that help make sense of all of this. Now you see what I mean and how this touches on a whole lot of the physics we've developed. Okay? That's what I want to wrap up the course with. I mean, it's a pretty simple introduction to what's called modern physics. But it's not all that modern because last century, even late in the last century, modern physics was older than I am now. Okay. Um, and by the end of the 20th century, what was modern physics had been superseded in many ways. But it was the foundation. Big deal. Okay, now let me take a quick look at the problem sets and make sure I'm giving you something that'll help you make sense out of them. Okay, back in the late 80s, before your grandparents were born, I taught a modern physics course at Emory and Hebron to juniors and seniors, pretty good students. And we did the thing in that lab. Okay, same thing we're going to do Friday, and it only takes a few minutes. Okay. Never could get the right results. It's an easy experiment. It's really straightforward. So, just like the other day in lab, managed to observe a nice exponential and an RLC. Okay. And you guys managed it. I didn't. I mean, I played around with it and turned you loose. You made the adjustments, and that was very good. It's really happy to see that. It gave us a good estimate of what our overall ought to be, what your time cost ought to be. Decent estimate. If this is two slits, so imagine I've got this rectangle of material. I put a slit here and a slit here that light can get through. Okay, or if this is a breakwater on a big lake or an ocean, waves come in. Okay, and you can make the analogy with electromagnetic waves. Okay, so what we have is wave fronts coming in here. Let's just say wave peaks. Okay. Well, the way these are spaced, at this instant, a peak's going to be hitting here and a peak's going to be hitting here. Right? Which is going to raise the water here and raise the water here. Now, if you raise some water and release it, what happens? You get ripples. You go out in all directions, right? Okay, just take a cylinder of water, put it over a pond, and then remove the bottom of the cylinder and let that water drop in, just like a pebble dropping in. Okay? So that peak is going to be there, but then half a cycle later, there's going to be a valley there. It's going to be down. It's going to be going up and down, creating ripples. So what you get is you got ripples coming out from here, coming out from here. Keep going, keep going, keep going, keep going. Well, at the points where the peaks of these ripples from this slit meet the peaks of the ripples from this slit, you get waves of double the amplitude. Okay? You get reinforcement. And then kind of halfway between, you get destructive interference. So you get this choppy wave here. And of course, the breakwater took most of the energy out of these waves, and there isn't that much energy in this and this. So you're probably not going to get messed up there. I experienced that directly. Probably the closest I've come to dying since I was born. Okay. On a lake in Canada, starting out on a 10-day canoe trip in June 16th, which happened to be my daughter's birthday later on. Okay. That night, there was a killing frost in Blacksburg. So it was cold. Okay. Water is cold. There's an island that created this effect. And ignoramus that I was, there were three of us in a canoe. I'd been there before. It just headed straight on. And the canoe got swamped. One of the canoes got swamped. And there's some people on the island. These islands are mostly uninhabited. But this was the first lake in a series, and they came out and pulled people in. Now, this was the first time that happened is in like August, and the water temperature was just like, oh. In June in Canada, water doesn't get very warm. And on a day when it's snowing, it's bad stuff. And I made the mistake of not plowing forward, but turning around and heading back. If you turn a canoe around with its back to the waves, it's going to get turned parallel to the waves and swamped. So, fortunately, I was in pretty good shape. But it's an educational experience. One of the guys really did get in trouble. There were three of us, all about the same height. One of them was about 210 pounds. There was me at about 170. And there was a skinny guy. I looked like a skinny guy, but he was a skinny guy. At about 130. And I was shivering hard enough that when I cut his belt off to help get him out of closing in some dry stuff, he couldn't move. And I ran a knife into my arm right there. Didn't bleed. Talking about thermodynamics. Think about it. Stay out of cold water. And the big guy was out there fishing our stuff out. When I got us over to the island, said, hey, come on in. It's not that bad. I was not inclined. And Elowitz was totally. Okay, anyhow, for whatever that's worth, can you imagine those peaks and how choppy it gets? Okay. Well, now if you put a screen over here, that there are going to be places that are equidistant from these two slits. Okay. At those points, the peaks are going to join everywhere along this line and everywhere along this line. I don't quite have that drawn right, but you get the idea. Okay. So you're going to get big reinforcement. Okay. Now, if you have unequal paths, running out of colors, Got my T and H mixed up, but 1/2 wavelength. Half a wavelength longer than the other. The waves cancel. That makes sense. It means peak travels from here to there. Peak travels from here out here, but it's going to be half a wavelength in front of this peak, which means that the peak's going to meet a valley. Okay? You can extrapolate this picture into a picture like this, where you got two closely spaced slits, a distant screen. Here's the path from one slit. Here's the path from the other. This a right angle. In this picture you have here, enlarged, looks like this, where these two, if this is a distant screen, are almost parallel. In other words, if you're firing a gun and you're going to shoot from here to that point, how are you going to have to change your aim if you move over to this slit? You're going to have to move the sight just a little tiny bit, right? So you're shooting almost the same direction. Does that make sense? Or if you're going to run from here to there, okay, or you're going to run from here to there, you just have to turn just a little slight bit. So you're going to run practically parallel paths. If this is a right angle here, then this is your path difference. Okay? Make sense? And if that path difference is one wavelength or 10 wavelengths, except the whole number of wavelengths, then peaks are going to meet peaks out here. If it's a whole number plus half a wavelength, then peaks are going to meet in valleys. Not difficult to understand if you get the image. Okay? And we can quantify that. Okay, this dotted line is perpendicular to the plane of the whatever it is you got the slits in. And here's your angle theta. Well, by simple geometry, which you want to think through, because I'm not going to think it through for you. Just want to exercise you a little bit, okay? One of the angles in this triangle is equal to theta, because this is perpendicular to this, okay? And this is perpendicular to this. So it should be pretty obvious, it looks right, at least, that you're in your picture for your path difference. Right here's your angle theta, and that was a bad place to label it. See why in a minute. There's your angle theta. And here's distance A. A is the separation of the slits. And the path difference Well, look at the picture. Here's your path difference, right? And of course, this is a right angle here. So everybody write down what the path difference is. Now, you should be familiar enough and have used enough trigonometry that it's obvious. So think it through pretty regularly, try to make it obvious. Here's your right angle, so here's your hypotenuse, that's A. Here's your angle theta, here's your path difference. It's the opposite side, so it's A sine theta, right? Constructive interference. A sine theta equals n lambda. That fraction you can't read there's 1/2, just like this one. Add half a wavelength, and you have peaks meeting valleys. So peaks meet peaks. Valleys meet valleys. Peaks meet valleys, sorry. We actually do this with a handmade diffraction grating. We have people line off a piece of paper with regular lines. Then I took it to the copier, transparencies, miniaturized it down to about, a whole sheet of paper, down to about this, with maybe 10 lines per, well, maybe 8 lines per centimeter, something like that. It made the lines and the spaces between them made something like 2 slits, but you have a whole bunch of them. So that the points where you had constructive interference are very sharp. In the points where you had any kind of destructive interference, had almost randomly distributed degrees of destruction. So that what you get when you shine a laser through this thing is basically a bunch of bright spots that you can measure, put a ruler on them, measure the distance between bright spots. Now, what you got is you got this grating here, you're shining a laser on it. So you got this beam going on to this thing, and here's the other end of the room, and that's where these spots are. Okay. The ratio between this distance and the spacing is the same as the ratio between this distance and the wavelength of the light. Very, very simple ratio that I'll explain in lab when we do this, but I want you to think through this because this is how you measure the wavelength of electromagnetic radiation. You run it through a bunch of slits and you look at the spacing of the maxima. Okay? That should make some of the stuff you're seeing in the problem set real. So read through those problems, at least the first half. And I'd read through the whole thing. Just take a scan of it and see what's relevant to what I was just talking about and start thinking about it. Okay? Talk more about it on Wednesday.